Okay, so on YouTube there's this interesting Newton's cradle experiment with uneven masses with a mass ratio of 3:1. So let's first hear Gary's prediction about the velocities after the collision.
All right, so my argument would be is this one clearly doesn't have 150 momentums, but whatever. And that really what it's done is taken 75% of the energy is now moving the 3 mass, and 25% is what you get as a reflection. So you get a minor amount of energy back.
So we have two predictions here. One is according to the conventional theory, using kinetic energy and momentum as a vector, so that direction matters. And according to this theory, the velocities after the first collision will be 1/2 of the initial velocity. And so kinetic energy and momentum as a vector will be conserved. You can check this and make the calculations yourself if you want. Then we have Gary's theory, saying that the 3 mass ball will end up with 75%, 3/4 of the initial momentum, and the 1 mass ball will be reflected with 1/4 of the initial momentum, meaning that the velocities will be 1/4 of the initial velocity. And here momentum will be conserved as a scalar, so that direction doesn't matter. Okay, here I'm going to make the measurements. I'm going to measure the distance traveled between 2 frames. Here we have the 1 mass ball, which has been dropped, and the 3 mass ball, which is stationary at the moment. And let's try to get it moving. So here we have the collision. I think the best distance to measure is this one, before there's any contact between the balls. So the 1 mass ball is about here, so let's draw a line. Next frame, and now we are here. So this is our initial velocity for the 1 mass ball. Then we have the collision, and I'm going to measure these distances. The 1 mass ball is a bit blurry on this side, so I think I'll make the measurement on this side now. So we are about here. Next frame. And now we are here. According to the conventional theory, this should be 1/2 of the initial velocity, and it's looking pretty good. So this is the 1 mass after the collision. And then we'll do the same for the 3 mass ball. So let's draw the first line here. Next frame. It's a bit blurry again, but I think the place is about here. So this should be the same size as the 1 mass after the collision, and oh, they are actually matching perfectly. which is of course partly a coincidence because there's so much uncertainty in the measurements, but still it's pretty good. So this was the 3-mass ball after the collision. So I would say it's already quite clear that these two distances or velocities are much closer to being 1/2 of the initial velocity instead of being 1/4 of the initial velocity. But we can also take a closer look. So we'll add these grid lines here and zoom in a little bit. Let's make sure that these left lines here are in line with each other and also with one of these grid lines. So let's move these a little bit to the right. Now they are matching. And now we can calculate the distances. So here we have 1, 2, 3, 4, 5, 6, 7, 7 point something, 7.3 maybe. 3 or 2, let's say 7.3. And here we have 1, 2, 3, well, 3.5 or 3.6. Let's say 3.6. I don't know how visible these grid lines are in the final video, but let's hope you can see something. And here we have, oh yeah, we had exactly the same length here, so also 3.6. Or 3.5, I'm not sure, but still they are both pretty close to being 1/2 of this initial velocity, and certainly not 1/4. We can also calculate what these values should be according to Gary's theory. So if we divide this by 4, we have, I have to get a calculator. So 7.3 divided by 4, that's 1.83. And also, according to the conventional theory, it should be 1/2. So if we divide it by 2, we get 3.65. So yeah, the conventional theory gave us much better prediction about the velocities than what Gary's theory did. Okay, that was it.